The authors investigate the ability of generative transformer models to perform deductive reasoning from provided premises, observing significant differences in performance among models from various training setups. They find that deductive reasoning ability increases with model scale, except for OpenAI GPT-3 and GPT-3.5 models, which show a decrease in performance with the length of the deductive chain. The study considers a wide range of transformer-decoder models, varying in size from 117 million to 175 billion parameters. The authors assess large language models' ability to perform deductive reasoning and examine how they fare as the size of the model and the complexity of required deductions grow. They evaluate the models in a setting where the model is provided with a context of premises and asked a single yes, no question, adhering to 4 specific conditions. This research paper delves into the deductive reasoning abilities, draw, of large language models, examining how their size and training setup influence their performance. The study seeks to answer 3 key questions. 1. How does the draw evolve with increasing model size? 2. How does the draw depend on the number of deductive steps required to reach conclusions? 3. Do specifics of the training setup, such as model variant, dataset multilingualism, or dataset size, significantly impact the draw? The experiments utilize the closed-world variant of the rule-takers dataset, which contains groups of 100,000 randomly generated theories for depths ranging from 0 to 5. These theories are written in structured language and include yes, no questions that ask about statements provable in up to k deductive steps. The dataset also includes 2 special groups, Nat Lang and Bird's electricity, each containing examples written freely in natural language with appropriate punctuation. The study evaluates 16 models, ranging in size from 117 million to 175 billion parameters, to comprehensively address Q1. For Q2, all 16 models are tested for depths 0, 1, 2, and 3, observing any changes and scores. To answer Q3, the results of all experiments are inspected for patterns aligned with different training setups, considering factors like model variant, dataset multilingualism, and dataset size. The hypothesis guiding this study is that model size would play a decisive role in draw, model performance would quickly decrease with depth, and the role of the training setup would be negligible. The full dataset, runtime configurations, and code used in the study are made available for reproducibility. The research evaluates the deductive reasoning ability, draw, of large language models as they grow in size. It involves running inferences on open-source models and recent OpenAI models, analyzing their predictions for yes, no answers, and examining their behavior with and without leading examples. The study observes that larger model size generally leads to higher draw, although this effect can be influenced by training configurations. This contrasts with previous findings on fine-tuned models, which show decreased draw on unseen data requiring longer chains of reasoning. The results are presented in tables and figures, highlighting the complexities and nuances in the relationship between model size and DRA. The authors present the results of their evaluation of open-source models, focusing on their deductive reasoning abilities. They list models by family, with size increasing in each category, and use binary accuracy as the evaluation metric. The results show that many models perform similarly on deeper and shallower questions, with the OpenAI GPT-3.5 models showing an increase in performance. The authors address 3 research questions, investigating how performance depends on the number of leading examples, the number of deductive steps, and the specifics of the training setup. They highlight the outlier performance of Bloom 560 meters, attributing it to the multilingual training setup. The authors acknowledge limitations, including the consideration of token probabilities directly, and suggest fine-tuning the language modeling head for potentially higher accuracy. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. The rule-takers dataset comprises structured language theories defining various attributes and their relationships. For instance, Aaron is described as kind, quiet, and round, Fiona is green, Gary is big and green, and Harry is quiet. Conditional statements, such as, if Harry is round then Harry is young, and, if something is green and not round then it is white, form a hierarchical structure with questions of depth 0, 1, and 3, indicating the complexity of relationships within the theory. In contrast, the NAT-lang part of the dataset uses natural language to express similar theories. It states that cold individuals can remain nice, green and kind people are young and big, red and cold individuals are usually nice. Specific individuals like Dave, a gardener, and Tom, due to his weight, are also described. An example from Figure 4 demonstrates how the dataset can be used to test a model's ability to reason about these complex relationships and generate accurate responses. The evaluation on natural language datasets, detailed in Table 2, showcases the performance of various open-source models. Starting with the GPT-1 and progressing to GPT-2 in small, medium, and large sizes, as well as GPT-2 XL, Bloom 560 meters, Bloom 1B, Bloom 3B, and Bloom 7B. The results demonstrate binary accuracy relative to a baseline coinflip performance of 50%. The metric used measures the proportion of correct answers. Notably, the Bloom 7B model exhibits the best overall performance, while the GPT-2 XL model performs best within its family. This evaluation highlights the effectiveness of larger models in natural language tasks. The evaluation of OpenAI GPT-3 and GPT-3.5 models on structured language datasets is presented in this section, as depicted in Figure 1. The models are listed from Ada to Da Vinci, with their corresponding leading examples, less, and yes no random, YNR, question prompts. The evaluation metric used is binary accuracy, measured in percentage points relative to the baseline coinflip performance of 50%. The results are presented in Table 3, showing the performance of each model at different depths, ranging from 0 to 3. The GPT-3.5 Da Vinci model performs the best, with a binary accuracy of 26.28% at depth 0, and consistently outperforms the other models at depths 1, 2, and 3. The best performances are highlighted in the table. The evaluation was limited by the available information through the OpenAI API, which did not allow for a comprehensive assessment without leading examples.